Good day to you. This is teacher Leland, Alejandro, and we're going to do graphing sine and cosine. These are trigonometric function sine and cosine. We're going to use the Desmos graphing calculator. So we shall see the graphing calculator screen right away. So we're going to use this, and you can see the display on the x-axis by natural numbers 1, 2, 3, 4, 5. We're going to change this to an increment of 45 degrees, or pi over 4 in radians. So you're going to make use of the wrench at the upper right side of the screen and click that, and then with the x-axis step increment, we shall make use of the pi over 4 there. So that is 45 degrees, and this is pi over 4 radians. Now make sure you are set to radians. So make sure the radians is in the green color, and then you click the wrench again to extinguish the menu. All right, and so this is now our graphing screen, and this will be for the y, okay, and this will be for the x. Now we shall plot the points starting with 0. That will be the input x, and then we will use sine of 0 there. Okay, and so you can see the point at the origin. All right, so this will be a manual first, and so we shall increment by, say, 0.25, and then sine of 0.25 there. And next is we shall make use of, say, 0.5, and then sine of 0.5 there. And then make use of 0.75, sine of 0.75 there. Next is, say, 1, and then sine of 1 there. And you can see, you can take note of the dots on screen, okay, the different color dots. This will form the sine graph, okay. Next is 1.25, and then sine of 1.25. Yeah. Next is 1.5, sine of 1.5, and then next is 1.75, and then sine of 1.75. Yeah. Next is 2, and then sine of 2. Okay. So the first number that I type, these are the x values. Okay, and then the sine of that value of x is the y. Okay. Next we have 2.25, then sine of 2.25. Yeah. So we shall put here parentheses. Yeah. Next we have 2.5, sine of 2.5. Yeah, and you can see the graph forming on our screen. Next is 2.75. That would be for the x. And the next x value will be 3. And then sine of 3. Yeah. Next x is 3.25, sine of 3.25. There. Okay. Next we have 3.5 for x, sine of 3.5 for y. And then 3.75 for x, sine of 3.75 for y. Okay, there. All right, and so next is 4. That will be the x, and then sine of 4. Remember, we're using radians, okay? Radians. And so we have here 4.25, and then sine of 4.25. Yeah. Next, we have 4.5 for x, and then 4.5, sine of 4.5 for y. There. And you can see our graph, okay? All right, it's forming, okay? This is what you call the sine graph, okay? Sine graph. All right, let's continue with our points. Next is 4.75 for x, 4.75, and then sine of 4.75. There. Then we're now doing the 5 as x, and then sine of 5 for the next point, and then we have 5.25 sine of 5.25. There. Next, we have 5.75 for x, sine of 5.75 for y. We should have 0.5 first. So this will be 5.5 and sine of 5.5 there. All right, that should be it. And next will be the x value 5.75 and then sine of 5.75. So we're using an increment of 0.25, okay, radians. All right, so well, I thought of doing that so it will have more points. Okay, now we shall have one cycle. Okay, from 0 to 2 pi. Okay, 0 to 2 pi. Next is 6. This will be 6, and then sine of 6, and then next is 6.25 sine of 6.25. Yes, there. All right, so just one more. Let's have 6.5 and have sine of 6.5. Yeah. All right. Okay, this approximates one cycle. Okay, so this approximates one cycle. Now, this is the manual graphing. Okay, computing each um, points. All right, each of the points on the graph. Okay, so each of the point on the graph, and then if you want the entire graphs very smooth, then you will have to type the actual equation, y equals sine x, or simply sine x there. Okay, and that completes the graph. So without this, it's just our points there. Okay, all right, and you can see those points there. These are actually our computed points. Okay. Now, if you want the actual smooth graph, then you can use the actual function sine x there. Okay. All right. So this is the manual graphing. Now, let us study the components of the sine function. Okay. Let's extinguish all this. Okay. Let me erase it. And then let us start with the discussion of amplitude and the other things about the function. All right. Now, we can start with the function, okay? Y is equal to sine x, okay? Now, you can see the number in front of this. You can see the number in front. This is y equals sine x. Then the number in front of the sine x is actually 1 there. Okay, that means 1 times sine x. And that number 1, which you don't see normally because we don't usually write the number 1, that is actually the amplitude, okay, the maximum value, the maximum value. And it is equivalent to the highest value over here, okay, that is actually equal to the highest value, okay, and then from this highest value, subtract the lowest value, okay, and then you divide by 2, all right, and that is the amplitude. This amplitude is this length here, from here there, that distance, okay, so that is actually 1, okay, that is 1, that particular height, that's 1, so that's what you call the amplitude, okay, that's the amplitude. All right, so if we change this 1 into some other number, say for example, we will change this to 2, then you will have the amplitude change, okay? The maximum is now 2 from the midline, okay? The midline for this equation, the midline is the x-axis. This one. This is the midline. Okay, the midline. And so the magnitude 2 is from the midline to the highest part of the graph there. Okay, that is the amplitude. Okay, and it's equivalent to the highest minus the lowest. Okay, divided by 2. Okay, so highest, that's the maximum, minus the minimum. Okay, the difference divided by 2, that gives you the amplitude. This is the amplitude there. Okay, all right, so that's clear enough. And so you just have to change that particular number coefficient in front of the word sine. Okay, so if you change this to 3, then you will have maximum of 3 there. You can see the height. Okay, it's on the third level. Okay, all right, you can see it on the third level there. Okay, so the maximum now is 3, and you call this the amplitude. Okay, the amplitude. All right, so what if you provide a number there which is less than 1? Okay, what if you provide less than 1? Well, the effect is just the same. So for example, if you put there 0.75, okay, so we will zoom in so you will see it. Okay, what's the effect of 0.75 here? 0.75 there. Okay, it's less than 1. Here is your number 1. Here is your number 1 level. Okay, and you can actually see the 0.75 over here. This is 0.5. This is 0.5 level. This is 0.75 level there. Okay, you can see the 0.75 level. It's the maximum now. So the amplitude tells how high the sine wave will be graphed. Okay, all right, so you can see there it's 0.75. All right, so this is all about the amplitude. Okay, the amplitude. All right, so let us discuss now the period. Okay, the period. All right, so let's go back to the original equation. Let's go back to the original equation. Okay, our original equation is sine x. Okay, and let's concentrate on the number beside the x. So what we have here, I am going to write it down. Okay, what we have here is y equals sine x there. Okay, the coefficient here is 1. So it's 1x. Okay, 1x. In a formula, that is a sine b x there. Okay, and the number b is for the period. Okay, it is related to the period. Now the frequency, okay, is equal to b over 2 pi there. This is the frequency. Okay, the frequency is the number of cycles per period. Okay, all right, and so by using this formula for the frequency, the number b here is 1. Okay, so using this formula over here, that means our frequency is equal to 1 over 2 pi. That means we have 1 cycle per 360 degrees or 2 pi radians. So where can we find that? It's over here. You can see this particular length. Take note of this. This is 2 pi over here. That's 2 pi. All right, it's 0 to 2 pi. This is one cycle there. That's one cycle. Okay, so that means one complete cycle. Okay, because this is a periodic function. Okay, this is one cycle. The next part there will be another like this. Okay, and so for every 2 pi, it's one cycle. That's the meaning of frequency. Okay, so you can see this is one particular cycle there. All right, so that is the frequency. Okay, one cycle per 2 pi. All right, now let's change it. Let's put another number other than 1. Okay, let me clear my writing. All right, what if we change this to 2? Okay, say for example this is sine of 2x. There, sine of 2x. This time our b is 2 from y equals sine bx. Okay, our b this time is 2. Okay, all right, now the formula for the frequency will still be b over 2 pi there. And so if we compute our frequency, if we're going to compute for our frequency, then it's let's use this. Okay, we're going to use this. This is now 2 over 2 pi there. Okay, and where is this? All right, here is your 2 pi there. That's your 2 pi radians, or 360 in degrees. Okay, what do you mean by 2 per 2 pi over here? What do you mean by 2 per 2 pi, or 2 for every 2 pi? Okay, it's this one. All right, it's this one. 1, 2. Okay, so there are 2 cycles for every 2 pi. Okay, so one complete period and then another. Okay, all right, let me clarify that. All right, here is your 2 pi. Here is your 2 pi there. Okay, all right, you can see that. Now, according to our frequency, it's 2 cycles, or yes, 2 cycles per 2 pi. All right, so one cycle, another one there. Okay, so that's the meaning of this particular frequency. Now, what if you cancel out that 2? Because you can divide 2 and 2. So this will become, this will just become 1 over pi, right? You might say, oh, the 2 will divide. Okay, the 2 will divide. And so this will just be 1 over pi. Okay, that means one complete cycle per pi radians. That's also true. Okay, I can show you that. Okay, where is our pi? The pi radian is over here. There. Okay, and you can see it's one complete cycle. Okay, for every pi. That's the meaning of this frequency. Okay, all right. And so because this is one complete, this is periodic. Okay, the next part there is just the same as this. Okay, the next part here is the same as this. Okay, so this is periodic, it repeats. So 1 and then 2 and then they're all the same for every pi. Okay, for every pi it's one cycle. Okay, so that's the meaning of what we're talking about here. Okay, this is what you call the frequency. Okay, all right, so let's have another one. Okay, let's change that to say 3. Okay, so let's clear this, and then let's change our constant number coefficient for the x, say 3 there. Okay, all right, we're going back to our formula. This is y is equal to sine bx. Okay, Now, if you want the b now equal to 3, our b is equal to 3 there. Okay. Now, our formula for frequency, that will still be b over 2 pi. All right. And so we substitute our 3 over 2 pi there. Okay. 3 over 2 pi. All right. So where's our 2 pi? Okay, over here. There. There is your 2 pi, or 360 in degrees. So this is 2 pi radians. Okay, 2 pi radians. This is about 6.28 in decimals. Okay, because it's 3.14 times 2. Okay, so it's about 6.28 in decimals. That's the equivalent of 2 pi. Now, what we have this time is 3 per 2 pi. Okay, how can you see that in the graph? Okay, watch this. From the 0, okay, from the 0, all right, this is one complete cycle, and then another, and then another there. So you have 3 complete cycle. All right, that's one cycle times 3, and there are 3 for every 2 pi. Okay, and here's your 2 pi there. Okay, all right. So that's how to see the frequency. Okay, all right. All right. So let us now proceed to the horizontal shift or horizontal translation. Okay, this is called a phase shift. Okay, phase shift. So this is something like this. Phase shift. Okay, we're going to change something in our formula. All right, so let me clear the writings. I hope this part is clear. All right, now let's return to the original equation. Okay, so this will now be x. All right, now if you're going to consider all the numbers in our formula, then we already discussed something like this. Y is equal to a times sine bx there. Okay, now we're going to add another. Okay, we're going to add another. All right, so let us use c. Okay, all right, let us use c. Now, if you have something like this, all right, that means a, the amplitude, times sine of b x. Now, what if we subtract something from the x? Okay, subtract. All right, say y is equal to a times sine b x minus, say, let's say uh, h, something like that. Right? Okay. Now it depends on the h. Okay, if your h is positive, this sine graph will move to the right. Okay, it's going to move to the right. All right. Now let us see another form of this, and we shall transform this to another type of line. Okay, so let's say we are going to change this to something else. Say let's transform this to a hidden line like this. All right, you can see it's a hidden line. Okay, to distinguish it from our next graph, and then we shall try another. Say y is equal to sine. Okay, and then we shall subtract something from the x. Say minus 1 there. Okay, all right. You now have two graphs on screen. The hidden type, the hidden line type, and then the object line type. Okay, the blue line. All right. Now we shall try to locate a point okay, which is just moved to the right, okay. So remember, our original is the hidden line graph, okay. All right, let's consider the same point. Let's consider the same point. All right, this point here, okay, watch the cursor. This point here is pi over 2, okay, pi over 2. All right, so let's remember that this number here is pi over 2, okay. Now let's consider the other point here, there, okay. This time it's the blue sine graph, okay. What is the value of the x there? Okay, we can see the value of x, it's 2.571. You can see it there, 2.571. That's the value there in decimals. So 2.571. All right. Let's determine the difference. Okay. Let's find out if it really moved to the right. Okay. Remember, our original graph is the hidden line graph. Let's find out if it really moved to the right by 1 unit. Okay. All right. So we shall compute what is 2.571. What is 2.571 minus pi over 2? Okay, I'm trying to compute at the left side of the screen. Right? Let's see what we will get out of the computation. You can see the answer here. There. The answer is 1.00020. It's 1. Okay, so the blue graph is actually the second graph. That is with the horizontal translation to the right, okay, by 1 unit. So this is what you call the phase shift, okay. Now, if you subtract a negative number, then the blue graph will be to the left of the hidden line graph, green graph, okay. All right, and we're going to try that, okay. Let me clear this, all right, and let us now subtract, okay. Let me erase the blue. Let me do another one. So y is equal to sine of x minus a negative 1 there. Okay. All right. This time we subtracted a negative, okay, not just minus positive 1. All right. Let's see the effect of subtracting a negative. Did it actually move to the left or to the right? Okay. Remember, our original is the hidden sine graph, hidden line sine graph, okay? All right, so we can actually locate this point. Again, this is the same point, pi over 2 for x. Okay, there you can see it. That's pi over 2, and that location is right here. Okay, there. Now, what is the location of the other one? The same point. The same point, but just moved to the other side, okay? And that is this part here, there. All right, and that is 0.571, okay. All right, 0.571. All right, so let's find the difference, okay. Let's find the difference. This is 0.571, and it's actually right here. This is 0.571. All right, let's have pi over 2 minus 0.571, and how much do we have after doing that? All right, this will now be a computation pi over 2 minus 0.571. 0.571. All right, here's our result. Okay, it's 0.9997963. That is very, very close to 1. Okay, and so the graph really moved to the left. Okay. All right. So our conclusion is for horizontal translation, if you subtract some real number and it's a positive, your graph will move to the right. Okay. Now, if you subtract a negative number that is minus a negative, that means your graph will move to the left. Okay. All right, so easy to remember. If you subtract a positive, your graph translates to the right, and if you subtract a negative, your graph translates to the left. Okay. All right, so that is the effect of the third letter. Okay, remember, let's go back. Y is equal to A, that's for the amplitude, times sine of bx. The B is for the frequency, okay, and the period. All right, so if you include a third variable for the x, minus h, the h is for the horizontal translation. So A is for amplitude, okay? A is for amplitude. Amplitude varies the height, okay? It varies the height of the sine graph. Now, B is for the period or frequency, okay? It affects the period or frequency, okay? There. Now, the H is for horizontal translation, okay? Horizontal translation. I'll just put a letter T there, stands for translation. Now, we're going to consider a fourth letter, okay? A fourth letter. So this time we will add K, all right? This will now be for the vertical translation, okay? Vertical translation, all right? So that will be for our fourth. If you add something to this graph, okay, if you add, then it will either be go up or go down. Let me show you the effect, okay? All right, let me clear the screen. All right, let's go back to our original function, okay? And let's add something, okay? All right, just add, say plus, say 1, okay? Yeah. Let us retain the original, okay? All right. Let's retain the original. Say we go back to its original. So let's say we have this like whole number, an object line. Okay, let me see if I could change it to an object line. All right, let me start from the beginning. All right, let me start from the beginning. Say y is equal to sine x, okay? And then we shall make use of another y is equal to sine x. Say I'm going to add something plus, say, 1, okay? There, okay? So if you add 1, your graph goes up, okay? Now, what if we subtract 1? Let's do another graph. Going back to the original y is equal to sine x, let's say we subtract, say, minus 1 there, okay? So what do you notice? Our graph. So what do you notice? All right. Our original is the blue. Our green is plus 1. Our violet is minus 1. So if you add or subtract, it actually affects vertical translation, okay? Vertical translation. It's either become elevated or lowered, okay? That's the effect, all right? So we were able to learn amplitude, okay? The frequency and horizontal translation. And the fourth one is the vertical movement, okay? Vertical movement, either up or down, okay? So let's have a review, okay? All right. Going back to the y is equal to sine x, there. If you put a number in front of the function sign, okay, it will change the height, okay? If you put 2 there, it will change the height, okay? If you make it 2.5, then it will be higher, okay? If you reduce it to some number zero point 0.5, it will be lower, okay? All right? So that depends on the number you're going to place. Okay, so if it's just one, then the maximum is one there. Okay, the maximum is one. Okay, all right. Okay, now how about the frequency? All right, the frequency is the number you put coefficient of x there. So if you put there 10, okay, you will have a high frequency. If you put there 100, okay, you will have a very, very high frequency there. Okay, all right. So if you put there something small, then you will have a very low frequency. Say, say uh, 0.5, 0.5 there. See, it's uh, it's very low frequency. Okay, you can actually see this if we zoom out. Okay, zoom out there. So this is zero point 0.5 coefficient for x. So if you make this number more than 1, okay, you will have a high frequency. Okay, say I put there 50 there. That will be a very high frequency. Okay, all right. Now if you add something in front of the word sign, say 2, you will have a higher amplitude there. Okay, if you change that to 3, if you change that to 4, okay, then the magnitude changes. Okay, all right, that is for the amplitude. Okay, all right, let's go back to coefficient 1 there. All right, and how about the horizontal translation? All right, the horizontal translation, it will move, and you can only notice that if we do another graph. Okay, so let's do another graph with a magnitude of 4, and then sine say x minus say 3 there. Okay, so it actually moved by 3 units to the right. Okay, 3 units to the right, and you'll be able to check on that. You'll be able to check on that if you do a computation. Okay, if you do computation, so try to locate a point and make sure it's the same height. Okay, make sure it's the same height. So if you choose here, then choose somewhere here. There. Okay, if you choose here, then choose somewhere here. If you choose at the peak, then choose at the peak there. Okay, and then try to do a subtraction, and you'll be able to verify if it really moved by 3 units. Okay, but it can actually be you can actually just observe it, and it really moved actually. Okay, they're not in the same drawing. Okay, not on the same drawing. All right, so that takes care of the horizontal translation. So you can try another one. This is for sine, and then say x, say minus 2 there. Okay, all right, so this is the blue. Okay, so our original is the black. Okay, so you can observe it really actually moved from here, it moved there. Okay, remember our basis is the 4 sine x, amplitude of 4, and the number beside x is 1. Okay, our b. So that means our frequency is 1 for every 2 pi. Okay, 1 for every 2 pi. And you can see that here actually. Okay, all right. Just open your eyes. This is one cycle there. There's the 2 pi. Okay, that means one complete cycle for every 2 pi. Okay, 1 over 2 pi. That is when the number beside x is 1. Okay, all right. Now, the subtracted negative 2 is this. There. Okay, that is why from the black sine graph, it moved to the left. Okay, now how about the x minus 3? Well, we subtracted a positive 3. Okay, minus positive 3. So that means from this, uh, it actually moved here. There. That's the +3. There. Okay. That is comparing the red with the black. Okay. There. Okay. All right. So that is actually the horizontal translation. Now, if you're going to add something or subtract something to these graphs, this will move either up or down. That will be for the vertical translation. So let us subtract or add. Okay. Let's say we subtract 1. If we subtract 1 here, then it went down by 1. If you subtract 1 to the red, there, it also moved down. And if we subtract 1 from the blue, there. Now they're on the same level, okay? All of them. Let me clear my handwriting there. Let me clear my handwriting, okay? There. So you see, all of them move to a different midline, okay? A different midline. Now the midline is not the x-axis anymore, okay? It's 1 unit lower, okay? So that should be, the new midline must be the -1, okay? This line here, there. That's the new midline, okay? And still you have the amplitude 4, okay? The amplitude is still 4, okay? From the midline, this is 4, and going downwards, that is also 4 there, okay? So remember, the amplitude is the maximum height minus the minimum, and then you divide by 2. That is the amplitude, okay? All right. So how did you get the 4? How did you get the 4? Well, it is actually, all right, let's compute, okay? Let's compute from here. This is 3, okay? The minimum here is -5. So what I said is the maximum minus the minimum and then divided by 2, correct? All right, so 3 minus -5 divided by 2. And that is still 4, okay? 3 minus -5, that eventually becomes 3 plus 5, which is 8. 8 divided by 2 is 4. And that 4 is the amplitude, okay? There. And that's 4, okay? All right, so remember the formula. It's max, okay? So the amplitude is max minus mean minus the minimum divided by 2, okay? And make sure you include signs, okay? If it's -5 minimum, that will be minus negative, okay? And this is a +3, okay? All right, so that's how to compute the amplitude, okay? All right, and so how about if we make use of the cosine, okay? All right, let's see the cosine. Okay, let me clear the screen. Oh, before I forget, let's go back to the original sine and I'll show you something, okay? Just a graph of the sine function, all right? Okay, if you have y is equal to sine x, like this, okay? And let's go back to the original pi/4 increment, all right? You can see it here, all right? Now, if we increment the b, something that affects the frequency, say we put here 3, all right? And then, let's say we put here a 1, okay? And then take its absolute value, say absolute value of 1, okay? There, okay? All right, there. Okay, so you're going to have this kind of graph. Okay, there will be no negatives. Okay, there will be no negatives. They will be all positive, and this is how it will look like. Okay, this is how it will look like. So you can now increment the amplitude inside. Okay, there, and you can also increase the frequency, say 4 there, 5. Okay, and notice there is nothing below the x-axis. Okay, there's nothing below the x-axis. That means there are no negative values for y. Okay, because we have taken the absolute value. So instead of having the graph like this, instead of having it like that, instead of having it like that, then even the lower part of the graph is reversed because you have used the absolute there. Okay, and so this portion is not there because it went up there. Okay, this portion is not there because it went up there. Okay, all right, that's the effect of the absolute function. Okay, all positives. All right, and they do this in electronics. Okay, if you want to put all positive voltage, okay, using an input of alternating current, you will still have an output all positive there. Everything is positive. Okay, all right. So this is just one uh, application of the sine graph. Now let's have the cosine graph. Okay, let's have the cosine graph. All right. So we're going to change it to cosine, of course. So y is equal to cosine there. Okay. Now in comparing cosine with sine, all right, cosine starts with a maximum. Okay, it starts with a maximum over here. It starts with a maximum. So at a value 0, it's up there. Okay, and different from the sine function of which it starts from the 0. Okay, all right. So let's compare it. Y is equal to sine of x there. So with a 0 value, the sine is at 0 there. Okay, it's in this level. So that is the difference. Okay, cosine starts from the maximum. Okay, all right, it starts with the maximum. All right, so that's basically the only difference. Okay, that's the basic difference. So going back to the cosine graph, if you're going to plot the cosine graph, okay, it will be very similar to sine, but one cycle for the cosine is also 0 to 2 pi. Okay, and you'll be able to see it from here, from here and up to here. Okay, there, from 0 to 2 pi, that is one cycle. Okay, so this is one complete cycle there. And the next part there is just the same as this. Okay, the next part here is the same as this. Okay, so one complete cycle for the cosine is like that, from maximum to maximum, like that. So this is for the cosine. All right, so that's the only difference compared to the sine function. And cosine is an even function. It's an even function. It is symmetrical with the y-axis. Okay, all right, where is this symmetric with the y-axis? All right, I'm going to show you. This is the y-axis. That's why it's called an even function. Okay, it's an even function. There, it is symmetric with the y-axis. This is the y-axis. Okay, all points here will have equivalent all points there. Okay, all points here will be also there. Okay, so it's symmetric with the y-axis. and it's different. You call this even function. So the cosine function is an even function. It's an even function. Okay. Now the sine function is called the odd function. Okay. All right. So remember, cosine is symmetric with the y-axis. Okay. The right side of the y-axis will have an equivalent counterpart in the left side of the y-axis. Okay. It's balanced. Okay. Symmetric with the y-axis. Now, how about the sine function? How about the sine function? This is the sine function. Y is equal to sine x. Okay. Now, the sine function is an odd function. Odd. There. And this is symmetric with the origin. Okay. Symmetric with the origin here. Okay. Symmetric with the origin. Okay. How do you show that it is symmetric with the origin? Okay. One point to one side of the origin will have exactly the opposite. Okay. For example, this point here. All right. Its counterpart is right there. Okay. And a point here. All right. The counterpart of this point is right there on the other side. So it's symmetric with the origin. Okay. You call this symmetric with the origin. This is an odd function. Symmetric with 0, 0. Okay. And where is 0, 0? It's this. The point of origin there. Okay. All points here will have a counterpart directly opposite. Okay. Just remember 0, 0 is always a midpoint. Okay. It's midpoint. So this point will have another one over there. Okay. The point of origin is always a midpoint between those 2 points. If this point, okay, this is the other point, okay, and this is still the midpoint. It's still midway, okay, exactly midway between the two, okay. So if this is, you consider a point, the other end is here. The origin is still midway, okay, all right. And so this point over here, all right, has another point over there. And so this distance is equal to this distance. It's always like that, okay? And this distance is equal to this distance, all right? And this is equal to this, like that, all right? So it's symmetric with the origin, okay? This is the sine function, all right? Okay, so I hope I was able to explain the difference. So let me clear the screen. All right. So the cosine starts with a maximum. Why? Because the input, if you consider the manual graph that we did, okay, starting with 0, and then use cosine, cosine 0, all right, there's the point. Okay, you can see it starts with 1. Okay, the sine function started here. Remember, the sine function started here, and then it went like this. All right, that's how the sine function was graphed. Okay, all right. The cosine is different. Okay, the cosine is different. It's going to be from a maximum. Okay, from a maximum, it will proceed in a different manner. Okay, it will proceed like that from a maximum. Okay, all right. So let us do its graph manually first. All right. So starting with the input x, then we have 0.25 cosine 0.25. There's the point, the violet. Next is, let's use 0.5, and then cosine 0.5 there. And then next is 0.75, cosine 0.75. Next is 1, and then cosine 1. Next, let's use 1.25, and then cosine 1.25. There. Next, let's have 1.5 cosine 1.5. Next, let's say 1.75 cosine 1.75. There. All right. Try to observe the generation of points there. Next is 2 for x, cosine of 2 for y, and 2.25 for x, cosine 2.25 for y. And then next is 2.5 for x, cosine of 2.5 for y. Next is 2.75 for x, cosine 2.75 for y. All right, notice the graph of the cosine function. Then we will proceed to 3, and then cosine of 3. And then next is 3.25, and then cosine of 3.25. Next is 3.5 cosine of 3.5. Next for x is 3.75 cosine of 3.75 for y. Next is 4, x equals 4 and cosine of 4. Okay. Next is 4.25 for x, cosine 4.25 for y. And then let's proceed to 4.5 for x, cosine of 4.5 for y. And then we have 4.75 for x, cosine of 4.75 for y. And notice the graph. Okay, let's pan our screen. So we shall be able to see the completed version. We will stop when we reach 2 pi. Okay, that will be about 6.28. All right, there. And it will be somewhere here. Okay, it will be somewhere here. Okay, that will be one cycle. All right, so it looks different from the sine function. Okay, one complete cycle is different from cosine. So we continue with our x. Next value of x will be 5. Okay, so from here we will have 5 for x, cosine 5 for y, and then 5.25 for x, cosine 5.25 for y. And then we're almost done. 5.5 for x, cosine 5.5 for y, and then 5.75 for x, cosine 5.75 for y. Next is 6. We're already in the 6 for x, cosine 6. And then next is 6.25 cosine of 6.25. All right, we're almost done. Okay. All right. Remember, 2 pi is 3 times 3.14. So that's about 6.28. And we are now in the 6.25. So this is close enough to 2 pi. And we can stop here. Okay. And this is one cycle for the cosine function. The next part will be just a replica of this. Okay. So this is one cycle. This is one cycle. The next part there will be the same. Okay. It's a repetition of this. Remember, we're dealing with the periodic functions. These are periodic sine function, cosine. These are sinusoidal function. Okay, and so if you want this smooth, all right. If you want the graph smooth and not dots, well, we will have to resort on typing cosine x. Okay, cosine x there, and you will have your graph smoother. Okay, and this is actually the cosine graph. Okay, remember it starts with the maximum. Okay, all right, there. So one period is here. From here up to there. Okay. All right. So that's it. So this is how to do the sine and cosine graph. And the graphs for sine and cosine has both amplitude, uh, the period coefficient of x there, the b, and then the h for horizontal translation and the k for vertical translation. So I'm talking about this amplitude cosine bx minus h plus k. All right. This is amplitude. This is for the period and frequency. This is for horizontal translation, and this is for vertical translation. Okay. All right. So the effect will be the same as what we did in sine. And to cite some examples, let's do it. All right. So let me just clear first our points. Okay. Let me clear the points here first. Okay. Let me clear all the colored points there. Okay. Now all the points are gone. Okay. Let's say we have this is the parent graph. Okay. Again, if you put here a number one, the amplitude is 1. Okay, you can see the highest, it's 1. There, that's the level. From 0, okay, that is 1. That's the maximum. Okay, now if we change that number, if we change this number, say we make it 2, all right, we will have an increase. Okay, we're going to have an increase just like the sine function. And your maximum now is 2. There. All right. If you change this to 2.5, change it to 2.5, then you will have a maximum of 2.5 there. Okay. It's halfway between 2 and 3, halfway there. And from 0, that's 2.5 there. So the amplitude is the same as in the same effect as in the sine function. Okay, now the numbers you put as coefficient of x will affect the frequency. Okay. Okay, so if we put some numbers here, say instead of 1x, because this is really 1 times x there, it's 1 times x. Okay, and that means one complete the same computation for the frequency for the sine function. So if the number is 1, then the frequency is the same. The frequency is b over 2 pi, and that means our b, it's over here, our b is 1. Okay, so that means 1 complete cycle for every 2 pi there. Okay, and where is that? You can actually see it here. This is 1 complete cycle there. That's 1 2 pi there. It's from 0 to 2 pi there. There's the 2 pi. Okay, I hope you can see it there. There's the 2 pi. You can see it there. Okay, and this is 1 complete cycle. This is 1 complete cycle. Okay, from here to here. There. That's 1 complete cycle. Okay, so that's the meaning of this b. Okay, it's 1 complete cycle for every 2 pi. What if we change this number b to a number 2? Let's clear it. What if we make this 2? Will it be just like in sine function? 2. Okay, all right. That means 2 for every 2 pi. Okay, 2 for every 2 pi. And where is this? Let us change the amplitude so we can see everything clearly. Say we will stick to just 2. All right. Where is this 2 per 2 pi? Oh, well, our formula is the same. It's the number b divided by 2 pi. There. All right. This time our number is b equals 2. There. Okay. So this our frequency. This means 2 for every 2 pi. There. Okay. Where's our 2 pi? It's right here. There. Let's count uh, if there are two, okay, complete cycles. All right, this is one complete cycle for cosine. That is one, okay. All right, where's the other one? Okay, from here again. There, see, there are two. There are two complete cycles per 2 pi. All right, so this is the meaning of this. Now, if you reduce this to lowest term, instead of 2 over 2 pi, this looks like 1 over pi. Okay, 1 over pi. And where is that 1 every pi? All right, here is the pi. The pi value is right here. And it says here 1 complete cycle per pi value. Okay, this is 1 cycle for cosine. There, it stops here. There, see, it's 1 for every pi. Another pi added, this is another pi. There, that's why pi plus pi is 2 pi. There, okay? 2 pi radians, all right? Okay, so that's it. I hope you were able to compare this to the sine function, okay? You were able to compare this to the sine function. And I hope you'll be able to use this in your assignments and quizzes. So just the same, if you increase this b, you will have a higher frequency, okay? And let's see that. All right. If we make this number, if this number 2 here, if you change this number to a higher number, you will have a higher frequency, okay? All right, let us show that. All right, so if we make this say instead of 2, let's make it say just 20. There, see, you have a higher frequency. All right, and that's 20, okay, per 2 pi. All right, where is your 2 pi? Here's the 2 pi, I can still see it there. So here's the 0, okay, the point of origin, and then you can actually count that, okay, you can actually count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, I can see it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 cycles. Okay, there. Okay, remember, one cycle is from maximum to maximum. So this is maximum to maximum there, okay? So one like that is one count, okay? All right, so, and we have 20 like that from 0 to 2 pi, okay? So that means 20 cycles per 2 pi, all right? So that's how to see the frequency, okay? All right, and so that's it. So see you later for other algebra topics, okay? And this will be all for now, and see you later.